In this demo session, you will explore the full range of answer and meta capabilities for squeak and rattle analysis. We will begin with the answer preprocessor, where you will see how to identify areas that may be susceptible to squeak and rattle issues. Next, we will move on to setting up the E-line, and finally, we will demonstrate how to solve the model directly within Answer and generate a report evaluating the results. In the Meta Post-Processor, you will look at the updated tools for evaluating E-line results. We will also introduce the brand new Node Pairs Ranking tool, a faster and simpler approach to assessing squeak and rattle behavior. Let's start with Answer. In E-line identification area, we press Identify with the Clearance Analysis option. With this tool, we perform a solution 103 for eigenmodes, and then in the background, Meta Post-Processor runs to identify all the intersections in our model. The results of the evaluation are saved in a pickle file and are shown in ANSE with a fringe bar. In the pop-up window, we select a directory to input the results. Then, we must define the frequency range, the number of modes we want to extract, and an SPC set. We check the option Run Meta in NoGUI and we keep the default values. We can press the Calculate button to run the simulation. In case we have already done the simulation and we just want to load the results, we press here and we select the results file. We can see the results on our model. Then we can create 3D curves in order to proceed with the setup of the E-lines. A much simpler approach in identification of critical areas is the geometrical analysis. With this tool, we check our geometry by proximity, and if any properties are closer than the proximity value, then the tool automatically creates 3D curves. This is the result after pressing OK. We can examine the model and proceed with the setup of the E-lines. We press Pick E-line to select the 3D curves from the screen. Press the torch button to highlight the selected E-line. Check the option to automatically create the header for the solution. Select the master and the slave area. There is an option to automatically identify the master and slave area by proximity from the selected E-line. Also highlight button is available. We will select the gap option as there is gap between the two parts in our demo file. Then we select Rattle Displacement Based option and we define the values for spacing and search distance. In configuration, we select the in-plane option as the two parts lie in the same plane as you can see. Optionally, we can check the renumber option and define a start value for the nodes, the C-bushes, and coordinate systems that will be created. Optionally, we can also assign an offset value for the RB3 entities. Press Pick to select a starting point for the realization of the E-line. Optionally, select a name for the E-line. Press the Expand button to check the setup, and if everything is fine, press the Realize button. The E-line is realized with RB3 C-bush RB3 elements as we can see. Press the Erase FE button if you wish to erase the E-line. We can save the setup in CSV format by pressing the Save button, or load a previous setup by pressing the Load button accordingly. The mapping of the parameters is done by E-line ID as we can see here. After we've finished the E-line setup, we proceed with the solution setup. We select a path and a file name to save the results of the Nastran solution. We select All and we check the option Run Meta on Finish. With this option, Meta Post Processor will run in the background, evaluate the results, and creates a report. This list is updated with the E-lines from the previous step. For the evaluation of the results, we must define the values for the post-processing. In this demo file, we will keep the default values. We will select the option Use Existing Header. The header was created in the previous step automatically together with the realization of the E-line. We must edit it to define some values. Select the SPC set, the time step entity, and the deload BC set. Press OK to confirm and open again the tool. Press Run Solver to start the simulation. After Apellisys Solver finishes, Meta evaluated the results and creates a report as we can see in this example. Line plot, histogram, and evaluation contour plot functions are reported for both rattle and squeak directions for all the E-lines. Let's move now to Meta Post Processor. We will start with the updated E-line method toolbar. As solver, we select Nastran. In Geometry field, we must select the Nastran file and press Import. Then we select the punch file with the results and press Load. A window pops up, which prompts the user to select in which Nastran file the results correspond. In this toolbar, we can work with multiple Nastran and punch files, and for that reason, this match is crucial. We press OK. Now, if we select any E-line from the list, the corresponding Nastran and results file is shown in the fields above, as also the default evaluation parameters in the settings section on the right side. Check the entity identification on selection option to highlight the selected E-line in the 3D model. You can delete any imported model by selecting the E-line from the list and pressing the Delete Selected Model button. Edit any value and press the Apply button to confirm. Multiple selection is also possible for the settings application. Moreover, it is possible to save the settings in a JSON file or load them from an already saved file. We can select as many components we wish for the evaluation. I will select Z, magnitude, and major principal peak-to-peak components. Then I will select all the available evaluation functions in E-line evaluation section. Regarding the layout of the plots, I will select the option single E-line/multiple components, where for each E-line a new plot will be created with all the components. Save Configuration button saves the current image of the tool in JSON format. This includes paths and selections on the user's interface. Accordingly, the Load Configuration button reads the JSON file and recovers the saved status. With button Reset All, the toolbar returns to its initial status and a new meta session is created. Press the Create button to show the evaluation results. As we can see, two windows are created, one for histogram and one for line plot. On each of them, one plot is created for each E-line. In line plot, we can see the relative displacement along the E-line and component. In histogram, the maximum of relative displacement for each E-line and component. The relative displacement is shown also on the 3D model. Open the labels list to change the view between the different components. Let's move now to the second tab. The E-lines are available also in this list. Select one, and the master nodes of the E-line are available in the nodes list. In settings, define the number of modes and peaks as also the punch file that contains the eigenvectors from solution 103. Select one or more nodes. The selected nodes are identified on the 3D model. Select as many components as you wish. I will select the time displacement and in-plane displacement functions as also all the modal contribution functions. Press Create button to show the results. One window is created for each selected function. In time displacement, we can see the relative displacement of the selected master node with the corresponding slave node a long time. In plane displacement shows us the relative displacement on the XY or squeak plane. The black line shows the major principal direction of the displacements. Relative modal contribution per peak shows the three most contributing modes for each of the three highest peaks. E-point evaluation shows the three most contributing modes of the selected point. E-line evaluation shows the three most contributing modes of the selected E-line. Let's see now a new approach in evaluation of squeak and rattle results, which is based in frequency domain instead of time domain of E-line method. Moreover, no special preparation is required in preprocessor, just a setup for solution 111. For this new approach, a completely new tool was designed. The main parameter to define here is the search distance. A default value of 3 will be used for this demo, and as rattle metric we will use the peak DZ. Press Calculate button. As a result of the calculation, the tool identifies all the parts that are in proximity of less than 3 mm, as also the nodes of the parts that lie in the same distance, and it creates node pairs. For each node pair, the max risk is calculated by subtracting the peak DZ value minus the gap value. Note that the gap value takes into consideration the thickness of the parts. It is also possible to change the thickness values by adding tolerances in this list. Important is that the max risk index is also multiplied by the material factor values. Thus, if we know that a material has low risk of contributing to rattle or squeak, we can assign a very small value and the max risk value will be multiplied accordingly. Select a part pair from the list. Two plots are created for the worst case node pair. The first shows the local displacements of the two nodes in the rattle direction, and the second the magnitude of the relative displacement. Moreover, the node pair is identified on the 3D model and basic information are given to the user. If we want to examine more node pairs that belong to the selected part pair, we must switch to Node Pairs view. In addition, we can change the ranking from rattle to squeak. Then, the plots automatically change to local X and Y directions. If we also enable the sliding amplitudes option, we can see the magnitude of the relative displacement in squeak plane. In this case, the max risk index is equal to max sliding amplitude.